The Hopfield network, published in 1982 by John Hopfield, is a form of recurrent artificial neural network that has attracted significant attention in the field of computational neuroscience and artificial intelligence. Named after its creator, the Hopfield network is a type of associative memory model that can store and retrieve patterns by employing principles inspired by biological systems. At its core, the Hopfield network consists of a collection of interconnected neurons that work together to perform pattern recognition and recall tasks. Each neuron in the network can be in one of two states, on or off, which can also be represented as -1 or +1, respectively. The network's connections, or weights, between the neurons store information about the patterns it has learned. These connections are symmetric and can be positive or negative, reflecting the excitatory or inhibitory nature of the synaptic connections in real biological systems. The central idea behind the Hopfield network is the concept of energy minimization. The network operates by iteratively updating the states of its neurons until it reaches a state that corresponds to a stored pattern, or a stable equilibrium. The update process is based on the principle that each neuron adjusts its state to reduce the overall energy of the network. The energy function in the Hopfield network is derived from the weights of the connections and the current state of the neurons. The learning process of the Hopfield network involves the storage of patterns in its weight matrix. The weight matrix is typically symmetrical, with 0 diagonal elements. The patterns to be stored are presented to the network one by one, and the network adjusts its weights to minimize the energy function associated with each pattern. The Hebbian learning rule, which states that neurons that fire together, wire together, is often used to update the weights of the network. As a result, the Hopfield network can recall and recover the stored patterns from partial or noisy input. One notable property of the Hopfield network is its ability to perform content-addressable memory, which allows it to retrieve stored patterns based on partial or distorted cues. When presented with a cue that partially matches a stored pattern, the network iteratively updates its state until it converges to a stable state that corresponds to the complete pattern. This feature has made the Hopfield network particularly useful in applications such as pattern completion, image restoration, and error correction. While the Hopfield network has shown promising capabilities in associative memory tasks, it also has certain limitations. One of the main challenges is the issue of spurious states. Spurious states are unintended attractor states of the network that do not correspond to any stored pattern. These states can arise due to the network's dynamics and can hinder its ability to accurately recall the desired patterns. Efforts have been made to mitigate this issue, such as using modified energy functions or introducing additional mechanisms to improve the stability of the network. Over the years, variations and extensions of the original Hopfield network have been developed. Some of these modifications include the addition of external inputs, the incorporation of stochastic elements, and the use of different activation functions. These adaptations have expanded the capabilities of the Hopfield network and made it applicable to a broader range of tasks. The introduction of the Hopfield network brought forth new insights and techniques that influenced various aspects of AI research and applications. Here are some key ways in which Hopfield networks influenced AI during that period. 1. Associative memory. The Hopfield network's ability to store and retrieve patterns through associative memory mechanisms inspired further research and development in this area. It sparked interest in exploring different types of associative memory models and their applications in AI, such as content-addressable memory and pattern completion. 2. Neural network research. The Hopfield network played a crucial role in the resurgence of neural network research during the 1980s and 1990s. It demonstrated the potential of recurrent neural networks and provided a foundation for subsequent developments in the field. Researchers expanded upon the Hopfield network's principles and explored more complex and advanced neural network architectures. 3. Pattern recognition and image processing. The Hopfield network's pattern recognition capabilities and its ability to recover patterns from noisy or partial input influenced research in these areas. It provided a framework for developing algorithms and techniques for image restoration, error correction, and pattern completion, which became important in fields like computer vision and image processing. 4. Optimization and energy minimization. The concept of energy minimization, as employed in the Hopfield network, influenced optimization algorithms and techniques in AI. The use of iterative updates and energy-based functions for reaching stable states and minimizing energy paved the way for the development of optimization methods based on simulated annealing and other stochastic search algorithms. 5. Cognitive science and neuroscience. The Hopfield network's resemblance to biological systems and its application to modeling memory processes helped bridge the gap between AI and cognitive science. It spurred collaborations between AI researchers and cognitive scientists, leading to a better understanding of how neural networks could simulate cognitive processes and phenomena observed in the brain. 6. Inspiration for new models. The Hopfield network served as inspiration for the development of various new models and algorithms. Researchers explored variations and extensions of the original Hopfield network, such as Boltzmann machines, which introduced stochastic elements and provided new perspectives on learning and inference in neural networks. 7. Hopfield networks in hardware implementation. The principles of the Hopfield network also influenced hardware implementations of neural networks. The recurrent nature and simple update rules of Hopfield networks made them suitable for hardware realization. This led to the development of analog and digital circuits that could efficiently implement the computations performed by Hopfield networks, paving the way for specialized neuromorphic hardware. 8. Theoretical advances. The Hopfield network contributed to advancements in the theoretical understanding of neural networks. It provided a basis for studying the dynamics and stability of recurrent neural networks, attractor networks, and their associated energy functions. This theoretical work formed the groundwork for subsequent research in the field of dynamical systems and nonlinear dynamics. In conclusion, the Hopfield network, introduced by John Hopfield in 1982, is a recurrent neural network that utilizes energy minimization principles to store and retrieve patterns. Its associative memory capabilities, particularly content-addressable memory, have made it a valuable tool in various fields such as pattern recognition and image restoration. Despite its limitations, the Hopfield network has laid the foundation for subsequent developments in the field of neural networks, and has contributed to our understanding of the computational mechanisms underlying memory and information processing in biological systems.